Fluid statics. So today we are going to see this topic called fluid statics. It's a very important topic from IITJ point of view. See, fluid refers to either a liquid or a gas. So you can call even a liquid a fluid, gas a fluid. Statics implies we deal with fluid at rest with respect to container. So we are looking at fluid which is at rest with respect to container. This is very important. I am not saying fluid is at rest in ground frame, but fluid must be at rest in container's frame. That is what we classify as fluid statics. If fluid moves with respect to container, we call it fluid dynamics. For example, a pipe is there and water is flowing in that pipe, then that comes under fluid dynamics because with respect to pipe, water is moving, the liquid is moving. Now we will first start with what we call as pressure in a fluid, which is a very important discussion. Even though I said fluid is liquid or gas, we would focus ourselves on liquids here in this discussion, because gases are highly compressible. You can compress them. A gas can be compressed to a great level, whereas liquids we can take, at least for our discussion, as incompressible. So we are going to focus mainly on liquids, which to a large extent are incompressible. Gases, we will deal with them in another topic, which is thermodynamics. So we will look into gases in that topic. So right now we will focus only on the liquids. So our first discussion would be pressure. How pressure is defined? Pressure in a fluid. First, let us understand one thing. Suppose if I have a plate with area A and I have a force which is acting like this on the plate. Force is acting only at one point. In such scenarios, strictly speaking, I cannot define pressure. Okay, there is a very strong reason for this. Pressure can be defined when you have a plate of area A and the force acting on the plate is distributed like this. It is acting at every point on the plate. Suppose this force acts at every point on the plate, everywhere, there is no exception, and the totality of all these forces is F. Then I can define pressure as force divided by area, or force on unit area, force on unit area, or force per unit area. To put it in a more simpler way, on area A, the force is F. On unit area, means on 1 meter square, what is the force? This is called pressure, and that would be F by A. Okay, so pressure is force on unit area. So pressure can be defined when the force acting on the area is distributed. Okay, pressure can be defined when force on area is distributed and acting perpendicular to area. That's very important. So which means that suppose I have a scenario where I have a plate area A, but the force is distributed but acting like this. It's acting in a slant way on the area. Let us say the angle this force makes with vertical is theta. Then I define pressure as this total force perpendicular to area, so F cos theta by A. You must only take the force which is perpendicular to area in defining pressure. So sometimes we write it like this: pressure is F perpendicular by area. So to define pressure, one, you should have an area. Two, you should have a force which is perpendicular to that area. Then you can define pressure as F perpendicular by area. Now, this pressure is a scalar quantity and has no particular direction. It's a scalar quantity and has no particular direction. That is very interesting to understand. So let us see why it has no particular direction. See, the concept of pressure comes into picture when the number of molecules that we are dealing with in the liquid, or for that matter in gas, is quite huge. Suppose right now I am, let us say, in certain place in a room, and these air molecules, they are so huge in number, they are coming and hitting my cheek, my face, my head, my chin. So if I put my hand in certain direction, suppose my hand is like this, so the molecules are coming and hitting my hand, and of course they are reflecting. So there is a force perpendicular to my hand. We take molecules are spherical objects, so whenever they come and hit our hand, they exert a force perpendicular to the area of the hand. For example, if I have a molecule coming like this, when it is touching that wall or that surface, it touches like this. So there is a force like this in the normal direction on that wall. So similarly, the air molecules are hitting my chin, perpendicular to chin. They are exerting a force perpendicular to chin. They may come in any direction, but at the moment of hitting my chin or my cheek, the force is perpendicular to the cheek. So pressure really comes into picture when the number of molecules is quite huge. For example, if I orient my hand horizontally like this, okay, the force will be perpendicular to the hand due to air molecules. If I orient my hand vertically, the force will be perpendicular to hand again. Why is this? Because there are so many molecules which are randomly moving in all directions. So however you put the hand, the molecules always hit perpendicular to the area. So the force due to pressure is perpendicular to area. This is a very important point. For example, I dip my hand in water. So these water molecules are coming and hitting or wetting my hand. They are hitting perpendicular to area. If I start turning my hand in water, the force that is acting on my hand is always perpendicular to the hand, perpendicular to the area. Okay, so what I want you to understand from this is as follows. If I have a container, if I just have one molecule in this, only one molecule, one gas molecule, let us say, the concept of pressure fails. I cannot define pressure here. I cannot define pressure because we don't know when this molecule hits the wall. So there is no force on the wall of the container right now. The molecule must go and hit it. Only then there will be a force. But on the other hand, if there are lots of molecules, suppose I have 1 mole of gas which contains Avogadro, that is 6.023 into 10 power 23 molecules of gas are there. There are so many of them. 10 power 23 is a very huge number if you start writing it down. 1 followed by 23 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. You see this number? It's so huge. So if so many molecules are there, I can say with certainty right now on this wall, lot of molecules are bombarding. There is no gap. Like a swarm of bees attacking someone, some person. These molecules are attacking the wall. Right now, so many molecules are hitting the wall. In fact, whenever you see, you will see each wall is being hit by large number of molecules. So, under such scenarios, I can define pressure as force acting on this wall due to the molecules per unit area. So, we can define the concept of pressure. So, pressure really can be defined when number of molecules is quite huge and these molecules are undergoing random motion, so that whenever you put an area, there are always molecules hitting that area. There are always molecules hitting that area. So we can always say that there is force on the area perpendicular to it, and hence there is the pressure. So this point must be understood. To define pressure in a more rigorous way, I can even write pressure as dF perpendicular instead of writing F perpendicular by d area. This definition is more precise because pressure may change from point to point. Pressure may change from point to point. So this is more precise definition. in defining the pressure. But still, something must be understood. Suppose if I have an area, the force acting on the area must be still distributed only. Maybe lesser force is acting on this part and greater force is acting on this part, but the force should still be distributed to define pressure. So of course the pressure may change from point to point. Here on this part of the area there is lesser force acting on unit area, so pressure is less, whereas on this part there could be greater force acting per unit area, so pressure could be more. So this is very important to understand, that the force must be distributed for us to define pressure. Now, pressure really has no direction, but force due to pressure is perpendicular to area. See, pressure is F perpendicular by area. Pressure really has no particular direction because it is due to the random motion of molecules. No particular direction. But force due to pressure, that is F perpendicular, is PA. This is perpendicular to area. So for example, in the room where you are stationed, there is atmospheric pressure. The air molecules are going in random directions. They are hitting your cheek, your forehead, the top of your head, your chin, your chest, etc. These molecular motions are random, so they are hitting every part of your body. So the pressure really has no direction. If you say the pressure in the room is 10 power 5 Newton per meter square, atmospheric pressure, it has no direction. But when you put an area, the force due to the pressure is perpendicular to area. When you put an area, the force due to the pressure will be perpendicular to the area. Okay, so for example, if I have an area like this, the force due to air molecules will be perpendicular to area. If I have an area like this, the force due to the air molecules will be perpendicular to area. Let's see one thing. Let's calculate the force on our head due to air pressure. We know atmospheric pressure is 10 power 5 Newton per meter square. It has been calculated experimentally to be this. Suppose if I take the head of a person to be 8 cross 8 centimeter square, the area on the head may vary from person to person. Somebody who has a very flat head, the area could be more. But let us see the force due to air pressure on the head area, on the top of our head. That is pressure into area. It will be perpendicular to area. That means it is perpendicular to the head. So 10 power 5 into, let's convert this into meter square, 64 into 10 power minus 4, that is 640 newtons. That is 64 kg weight. So without your knowledge, it is as if 64 kg person is sitting on your head and you don't even feel it. In fact, the air molecules are hitting the top of your head with this force. The blood inside your body probably is also hitting with the same force, keeping your head in equilibrium. So you go to space where there is no atmosphere, no air pressure. Your blood inside your body will make the organs burst. The head will burst and all pieces will be flying in different directions, because the blood pressure is not being balanced by any other outside atmospheric pressure. So you must go in a space suit if you go into space. Similarly, if you go deep into a ocean, probably the ocean waters are going to crumble you, because the pressure there is quite huge compared to your blood pressure. Okay, so far so good. Now let us see how pressure varies with depth inside a liquid. So variation of pressure with depth inside a liquid. To make you understand this concept, variation of pressure with depth in a liquid. Let's try to understand this. Before I go into the mathematical aspect of this, let me give you the physics behind this idea. Suppose I have a very weird container, a container of this shape, and it is already filled with water. So this is all water. Now if I punch a hole here, definitely water is going to sprinkle out in the form of a small fountain. Now let us even if I punch a hole here, you will be surprised water might come out like this. Only condition is this level must be probably more than this container. So let us say water is still here. So water may come out as a sprinkle. Now suppose I put a lid to this container. This is the lid. And I start applying a force on the lid. Some force I start applying on this lid. That means I am pressing the water more. So if the hole was there here or here, here or here, the water would try to come out with more force. Why it comes out with more force? Because I am pressing it with a certain force on the lid. So by increasing the force on the lid, you can say I am increasing pressure in this location or in this location or in this location or in this location. Everywhere I am increasing pressure. Now look at the reasoning that I am going to give you. Instead of this lid, what if I put another layer of water? What if I put another layer of water? That means, what is the idea I am looking at? This is the container, some container. Already it has water. So there is some pressure at this location, at this location, at this location. If I put another layer of water here, this water is being pulled by gravity, so it would try to go down. In the process, it would press this water. It's like just like a lid on which we are applying force. So as a result, pressure here would increase, pressure here would increase, pressure here would increase. If I put another extra layer of water, the pressure at points 1, 2, 3 would be even more. If I put another extra layer of water, the pressure at 1, 2, 3 would be even more. In fact, if there is a hole at 1, water would come out with more force. If there is a hole at 2, water would come out with more force here. And similarly at this point. So by adding more layers of water here, the pressure at 1, 2, 3 is increasing. That means if there are more layers above a certain point, pressure at that point would be more. For example, let's take a container with a liquid. Here pressure would be more because there are so many layers of water above it. And the water here is trying to escape in all directions because pressure has no particular direction due to the weight of all these layers. If you take a point here, pressure here is lesser because there are only less layers above. There are only some 15-20 layers. Whereas if you see here, there are some 40-50 layers. I'm just giving some relative numbers to make you understand this better. So the more the layers of liquid above you, the more the pressure at the location where you are stationed, more the pressure. For example, at sea level, the pressure is quite huge because there are lots of air layers above your head, okay, till the point where atmosphere is ending in space. But as you start climbing a mountain, let us say Mount Everest, the number of layers above you is decreasing, so pressure is decreasing. So as you go to mountain peaks, their pressure will be very less. If you go further high, you will reach a point where the pressure is so less that you might start bleeding. The blood vessels start bursting and there may be nosebleed and so on. So it's very clear now that pressure varies with depth. So how are we going to do this mathematically? So let's look at that. So the tools that I am going to use in fluids is 1. Newton's second law, of course second and third law mainly. So the whole of fluids I will be using only Newton's laws, and of course work energy methods, which is just a extension of Newton's laws. Sometimes work energy is very convenient, but so I am going to do the whole of fluids with Newton's laws only in most of the cases. Your Archimedes principle is also a consequence of Newton's second law. We'll explore that in more detail. So suppose I have this container, I have liquid in it, liquid density is rho. What is density? Density is mass of unit volume of liquid. Okay, mass of 1 meter cube volume of liquid. that is density. Density of substance is mass of unit volume of that substance. Unit volume means 1 meter cube volume. Okay. For example, if 2 kg of a substance occupies 4 meter cube, unit volume, you take 1 meter cube, find its mass. That will obviously be 2 by 4. So that's how you got the formula mass by volume. This is mass, this is volume. Mass by volume is density. So here I took the density of the liquid to be rho. I have a point 1 in this liquid. I have another point 2 in the liquid. The second point is below the first point, and the distance between these points is h. So I want to relate pressure at 1 with pressure at 2. I know that pressure at 2 is more, simply because there are more layers of fluid above point 2, and pressure at 1 is less, simply because there are less number of layers above point 1, less layers above point 1. But I want to establish a mathematical relationship between 1 and 2. So what we do, we imagine this portion of fluid, which is in the form of a cylinder like that. Okay, this height is h. So this portion of cylinder we imagine, okay, it's a cylindrical portion of fluid, and we draw its free body diagram. So I am separately drawing this. This is the cylindrical portion of liquid. It's my imagination. It's a portion of liquid that I have assumed. Okay, and let's draw its free body diagram. The other liquid molecules, the surrounding liquid molecules surrounding this element, are coming and hitting this element like this with a force which is pressure into area P1A. You see the force is perpendicular to area. Similarly, from the bottom, the liquid molecules are hitting with a force P2A. At the sides also these liquid molecules are hitting, but that's a horizontal force. I am not interested in horizontal forces because I am going to apply Newton's laws in vertical direction. You can apply Newton's law in a particular direction. So I am only interested in vertical forces. And Earth is going to pull this fluid with a force which is mg, which is called weight of the fluid. And I don't see this imagination, this imagined fluid, whichever I have imagined here, which I have darkened. I see it is at rest, it is not moving. Okay, because this is fluid at rest. So any part of the fluid is also at rest. So if something is at rest, net force on it must be 0 from inertial frame. We are in inertial frame. So we must have P2A upward force is P1A plus mg. Okay, but we know mass of this darkened fluid, mass is density into volume, density is rho, volume is height into area. So I am going to plug in that instead of mass. So my m is rho h a. So I am going to put it here. So P2A will be P1A plus rho h a g. So you see I am using Newton's laws. I took portion of fluid. I see it is in equilibrium. I have shown forces on it. There is a pressure force due to surrounding molecules and weight due to earth. All these forces are keeping the liquid in equilibrium. So we have this relation. A gets cancelled. So I have the famous relation P2 is P1 plus rho GH. So as you go down, pressure increases by an amount rho GH if you go down by h. Okay. Why is this increasing? Because of gravity. Okay. If there was no gravitational force, then mg would be missing. Then the fluid layers do not have a tendency to go down and press each other. Then pressure would not change. So if you take a fluid into gravity-free space, the pressure at any point inside the fluid will be same as long as it doesn't accelerate. Okay, you take fluid to gravity-free space, keep it at rest. Pressure at every point in the fluid will be same because there is no pressing of one layer with the other layer, and so there is no increase in pressure. Now here in this derivation I have assumed a very important point, which is the density of the liquid is constant everywhere. I have assumed it as rho. There are cases where density may also change with depth and height. For example, for atmosphere, the density itself is changing The density at sea level is different, the density of atmosphere at Mount Everest is different. So if density changes, this derivation will fail. Why it will fail? Because if I take density constant, I can write this darkened mass as density into volume, like that, the mass of this. But if density is changing, then you can't write it as in this manner. You can't write the mass of this darkened fluid as rho HA. So then how would the derivation go? So let's look at that. So in such scenarios, this is the fluid, this is the point 1, this is point 2 separated by H. I want to relate pressure at 1 to pressure at 2, density not constant. Density not constant. So what is this case? So let us say this is point 1, this is point 2. At a distance y below point 1, I take a small disc whose thickness is dy. Okay, small portion of liquid. Okay, cylindrical portion only, but the thickness is dy. Okay, so we'll draw forces on this. So here there is P into area, pressure at that location. Here the pressure will be P plus dP because you went a bit below by a distance dy, pressure increased slightly. And this weight is given by the density at this location. At this location density is constant because it doesn't change much in dy. dy is after all tending to 0. So the density of the liquid at y and at y plus dy is same, which I take it as rho. Okay, so that's how we do in calculus. So density at that location at a distance of y, rho as a function of y, I would say. From y to y plus dy, it doesn't change much. Into volume, volume is A dy. So all these forces are keeping this very small cylindrical fluid element in equilibrium. So you must have P plus dP into A is PA plus rho, which is a function of y, into A into dy into G. I forgot about G, mg. So A gets cancelled. So we have P plus dP is P plus rho as a function of y into G into dy. This P gets cancelled. So we have dP is rho G dy. Of course, rho is a function of y. Integrate now. When y is 0, here we are at point 1. Pressure is, let us say P1. When y is h, pressure is P2. So we have P2 minus P1 is G integral rho dy from 0 to h. This is how pressure changes with depth if density is changing. If you check from this relation, there is a special case. If density is constant, a special case, then rho comes out of the integral. So then you have P2 minus P1 is rho G, integral dy will be y, it will be h. You get the relation. If rho is constant, you get back the original relation. If rho is not constant, use this at star, this relation, you use it. So that is how pressure varies with depth for cases where density is not constant. So obviously, now if you have a container with liquid, and let us say the container is not accelerating horizontally, container does not accelerate horizontally, suppose, then in such a case pressure at the same horizontal level will not change. So P1 will be equal to P3. How can we get it? Very simple. You choose a fluid element encompassing 1 and 3 like that, very small one. So this is the fluid element. Here the force will be P1 into A, horizontal force. Here the force is P to A. There is no acceleration, so acceleration is 0. Forget about vertical forces because I am applying Newton's law in horizontal direction. So apply Newton's laws. P1A minus P2A, net force is mass of the fluid into acceleration is 0. So which implies P1 equal to P2. So if fluid does not accelerate horizontally, pressure at the same level will be same. Please note, this is valid only if the fluid does not accelerate horizontally. Okay, so at the same level pressure will not change, it will be same if fluid does not accelerate horizontally. Which means, suppose if I have a fluid, suppose I have point 1, I have point 2, I have point 3, this is at a depth h. So I know P1 is equal to P2 and P3 is P2 plus rho g h. So you see it's varying only with depth. Horizontal level, at horizontal level pressure is not changing. Of course the container should not be accelerating. Acceleration of container equal to 0 horizontally. That's the important point. Then P1 is equal to P2. What about if I have a container which is a very weird shape like this and it is filled with liquid of density rho? How would the pressure change from point 1 to point 2? The answer is very simple. It depends only on the vertical height, which is h. If you are not convinced, you can do this. From 1, go horizontally, go vertically. Horizontally pressure did not change, vertically pressure increased by certain amount. Again go horizontally, pressure did not change, go vertically, pressure increased, horizontally pressure did not change, go vertically, pressure increased, horizontally did not change, vertically it increased, horizontally no change, vertically it increased. So all verticals, if I call this height h1, if I call this height h2, h3, h4 and h5, pressure increased by rho g h1 plus rho g h2 plus rho g h3 plus rho g h4 plus rho g h5, which is nothing but rho g into sum of all h1, h2, h3, h4, h5 is h. So it depends only on the vertical distance by which you are traveling. Only that is influencing the pressure. Of course the container should not accelerate horizontally. If it is accelerating horizontally, things are different, which we will look at in our further coming lectures. So thank you.